Greetings. My name is Edward Carter for Auburn University's COMP-6970, giving you a presentation on my proposal pitch for classification-aware distributed collaborative learning for Brigade-Level Intent Estimation with Pareto-Optimal Decision Support. A quick overview. This is a distributive learning collaborative learning with a military intelligence emphasis. It's a combination of federated learning, classification-aware privacy, and Pareto-optimal decision support. The intent is to enhance the brigade-level decision-making without breaching classification boundaries. The problem statement. I would like to hint on or emphasize on large-scale combat operations, which are described as intense and lethal military engagements involving multiple echelons of command against a similarly equipped adversary. Unlike counterinsurgency, which focuses on smaller units, large-scale combat operations emphasizes the combined arms maneuver and synchronization of capabilities across different domains to achieve strategic objectives. Key aspects include advanced technology, logistics, and the need for adaptable leaders capable of rapid decision-making in complex and dynamic environments. From that, let's move into contested environments. A contested environment being a situation where the adversary actively seeks to deny, disrupt, or destroy friendly force, logistics, operations, facilities, or activities across multiple domains. The domains being air, land, sea, space, and cyber. So, while conducting large-scale combat operations in contested environments, military units, specifically brigade commanders, need secure, multi-objective distributed learning to preserve autonomy and data sovereignty. The system hierarchy. While the global model resides at the brigade headquarters, local models, or nodes, will be trained at the battalion level. These nodes will be using ISR reports, human reports, tactical SIGINT reports, GEOINT supports, and other tactical operation debriefs. Those nodes will then be aggregated via encrypted model updates into the global model. At this point, the brigade commander will have the ability to determine the unit's course of action and how to commit his troops. The troops to commit outside of the battalions that are already engaged in the fight would be the cavalry squadron, who specializes in reconnaissance, surveillance, direct action, and act as an exploitation force, or the artillery battalion, which purpose is to disrupt, engage deep targets, destroy high-value targets, and provide non-lethal support. So we see how the federated learning algorithm can take what battalions 1 through 2, 3, 4 sees on the battlefield, aggregate it all together to determine what the enemy commander's true actions are. Is it a true attack or is it a feint? Is the commander using pressure to redirect forces or however? And thus he can commit his cavalry squadron, to either conduct more reconnaissance or to serve as a screening force, while the artillery battalion, to destroy or disrupt their movements. This problem has one major concern that has two categories, and that's classification. In this context, classification has two different meanings. Information classification, dealing with national security, and the model classification, dealing with the intent, activity type, and threat level of the enemy. A layered model structure by clearance levels ensures that no cross-domain leakage or spillage could occur. A model trained on unclassed data will always be unclassed. A model trained on top secret data will always be top secret. The federated learning framework. So each battalion trains locally with encrypted data. Again, it's aggregated, it's updated. The models are updated and sent securely to Brigade. Aggregation happens. The models redistributed with tiered access. Again, the classification levels. And the analyst performs verification and validation. For each predicted intent, the system surfaces supporting indicators from which battalion contributed the most to salient features and cues, i.e. time, locations, unit movements, logistics activities, recent engagement histories, from artillery to recce feedback, uncertainty sources, missing sensors, low sample counts. These enables the commander and the analyst to verify and mentally simulate the prediction before acting. The Pareto-Optimal Decision Support balances objectives from detection accuracy, being the model's ability to correctly identify enemy's intent or activity patterns, with false positive rate, how often the system incorrectly signals a threat, to latency and speed, the time taken for data input to actionable insight, communication costs, the bandwidth used to send model updates between battalion and brigade headquarters, classification, exposure, and security risks, the ability for sensitive classified information, the probability that sensitive or classified information could be inferred from shared updates. In similar terms, the system balances 5 goals: accuracy, false alarms, response speed, communication load, and information security. These goals compete with each other, meaning no single model can maximize all of them simultaneously. The result is that the Pareto font of trade-offs enables commanders to select the configuration that best aligns with its mission priorities. Another even more concrete example. Let's say there's a prediction of the model saying there's a preparatory attack. The probability being a 78% chance of a probability. 78.78 probability of attack. What does the commander do? What is his options going forward? Well, in mode A, where he has high recall, the 78% probability pops up, and his false positive rate being is tuned to 0.18. His latency tuned to 200 milliseconds, and the exposure high. Well, then the algorithm, federated learning, would recommend mass screening and prepare fires. But let's say he had to switch to mode B. I want low exposure, low risk, low exposure. The probability is then 0.62. The false positive rates being now 0.06, so I want the data to be as accurate as possible. Latency saying I'm of 350 milliseconds. being more than 200 milliseconds, saying, hey, I can take a little time for the data to get back, for the answer to come back. But I want the exposure low. Well, the model then predicts or recommends an increased ISR and watch posture. Basically, just one more example. If the brigade commander's current priority is force protection and legal thresholds require low false positive rates before kinetic preparation, the commander picks mode B again and tasks additional sensing. However, if speed and disruption are paramount and the rules of engagement allow quicker actions at higher exposure, the commander picks model A. So you can see by dialing in the accuracy, false positive rate, latency, communication cost, and exposure, classification exposure, security risk, how the commander can dial in courses of actions. The methodology for dialing in those numbers, we use the weighted sweep federated learning, which maintains the diverse Pareto-Optimal models, secure aggregation, and differential privacy applied to all updates, and the robust aggregation defense against corrupted data. Basically, think of the weighted sweep federated learning like adjusting knobs on a radio. Each knob controls how much we care about speed, security, accuracy, or bandwidth. We tune those knobs through multiple runs, then pick the clearest signal that matches our mission's priorities. So you can see on the right-hand side, the equation at top, L sub total equals W sub 1, L sub accuracy, and so forth. Those are the knobs we're tuning. We do the sweep. Multiple federated learning runs are executed with different weight combinations to explore the trade-off space among objectives. For example, item run 1 prioritizes accuracy. If you look back from the weights back to the equation, we see the accuracy, W1 sub L accuracy is 0.7, latency being a 0.1, risk being 0.1, and communications being 0.1. However, run 2 prioritizes communication efficiency. Although accuracy is dropped, it's still not as low as latency or risk, but we see communication has been pumped up. And then run 3 prioritizes classification and security. We see that W sub 3 is 0.6, while every other one is pushed back down. Each configuration is evaluated on a vector of performance metrics, representing detection accuracy, false positive rate, latency, communication cost, and classification exposure, respectively. The results from all weighted runs, form a set of non-dominated solutions, the Pareto front, representing optimal trade-offs, where improving one objective would degrade another. This enables commanders or analysts to select a model configuration in line with the mission priorities. Again, speed, accuracy, security. The evaluation plan. How do we know that we're successful? These 3 questions, I believe it gets after what the basis of the algorithm or this project, this proposal. Can the system improve decisions under real operational constraints? Being LISCO, being in a contested area. Does it maintain classification security? Are classified documents still within their enclave and there's no leakage or spillage? And then finally, can analysts and commanders trust its recommendations? To solve these, we use data sets, simulated beta data sets generated from wargaming tools or synthetic data-based on doctrinal patterns. Sanitize operational logs, historical data stripped of classified details. Each battalion gets its own unique subset of data to mimic non-IID conditions. This allows for each battalion to see a different piece of the whole battlefield. So it forces the algorithm to put them all together and create the picture of the battlefield and then come up with a course of action suggestions based off the commander's tuned priorities. The metrics. Well, we need accuracy, communication cost, and latency and classification exposure. But quantitative measurements, category predictive performance, accuracy, precision recall, will tell us how the data identifies the enemy's intent, how well he identifies the enemy's intent. Efficiency tells us the latency and communication cost would be what determines the efficiency, And this is how fast and network efficient the learning process is. Does it take too long for data to be pushed from the battalion to the brigade and for then the global model to be updated and pushed back down to the battalions? Security and privacy, classification exposure score, the differential privacy budget. How well does the model protect sensitive data? Human evaluation is going to be the analyst trust and the decision speed. Again, it's whether human analysts find the system useful and reliable. And then the Pareto evaluation, the metric would just be the hypervolume and front diversity, the quality and spread of multi-objective trade-offs, making sure that the model explores different areas of the space. The ethical and security framework, the Department of War and the Army has guidelines for applied combat AI or AI in combat situations. Human must always remain in command. You see that as a theme throughout. AI aids never replace human decision or authority. AI must respect laws of armed conflict and its recommendations. Users must understand when, how, and why AI was used in targeting or ISR. AI should revert back to human control if the data integrity or communications are compromised. And then finally, AI models must undergo validations not just for accuracy, but for compliance with the role and the ethical constraints. And in conclusion, this federated pipeline collaborative learning introduced classification-aware distributive learning intelligence architecture that enables secure multi-domain learning across the echelons. And the Pareto-Optimal Optimization improves decision transparency. The next step going forward would be field simulations, personalizations, and hardware integration. Pending your questions, this concludes my brief.